Welcome to the Tech Room, your weekly breakdown of all things semiconductors. I'm your host.
And I'm your co-host. This is The Deep Dive, brought to you by SBN Media Studio.
So today on the show, we have a really packed agenda. We are looking at a massive, massive squeeze happening right now in the leading-edge silicon supply chain.
Yeah, it's honestly coming from both ends this week. You've got intense export control enforcement and the just, frankly, brutal economics of 2-nanometer manufacturing on the supply side.
Right.
And then on the demand side, there's this intensifying memory supercycle. Literally every foundry is racing to package and power the next generation of AI accelerators. So let's just dive right in.
Let's do it. So I want to start with the supply side first because the latest data coming out about TSMC's pricing is just staggering.
Oh, you mean the $30,000 figure?
Exactly. So TSMC has apparently set its 2-nanometer wafer pricing at roughly 30 grand per unit for their early 2027 production ramp.
Which is pretty wild when you think about it.
Right. I mean, to put that in perspective for you guys listening, their 3-nanometer wafer was priced at around $20,000. So that is a 50% jump in cost just for moving to the next node.
And that's like the steepest single node price jump we have seen in decades.
Yeah.
And AOD, just for anyone wondering, is basically the industry term for a new generation of chip manufacturing technology. So smaller nodes usually mean faster, more power-efficient chips.
But getting down to 2 nanometers it requires two massive technological leaps, right? And that's what's driving up the price so much.
Right, exactly. First, they're being forced to abandon the transistor architecture they've been using for years, which is called FinFET.
Because FinFET just physically runs out of steam at that microscopic level. It just leaks too much power.
Yeah, the leakage gets completely unmanageable. So the industry's transitioning to this new thing called gate-all-around, or GAA architecture. And this involves building these microscopic ribbons of silicon, and they're surrounded by the control gate on all four sides to stop that electrical leakage.
Which means they need entirely new fabrication tooling.
Exactly. And the second huge hurdle is extreme ultraviolet, or EUV, lithography. This is the light they use to print the actual microscopic patterns onto the silicon.
And because the features on a 2-nanometer chip are just so unbelievably small, TSMC basically has to double the amount of EUV steps compared to previous nodes.
Yeah, and those machines, they consume massive amounts of electricity, and they're relatively slow. So double the EUV steps just means double the bottleneck.
Which equals massive expense. But I do have to push back on the impact of that $30,000 figure for a second.
Oh, okay, go for it.
Because that's just the headline price for the whole wafer, right? Companies like Apple or NVIDIA, they don't buy wafers, they buy the individual chips, the dies that are actually cut out of that wafer.
Right, the usable pieces.
Yeah. So if the wafer costs 50% more, but you are dealing with a brand new, highly complex manufacturing process, the yield of actually working chips is going to be terrible. Doesn't that just crush their profit margins?
Oh, it absolutely creates severe margin pressure. Think of it like a car dealership, right?
Okay.
Imagine they buy a fleet of 100 luxury cars straight from a brand new factory. But because the factory is still, working out the kinks on the assembly line, maybe 30 of those cars roll off the lot with totally defective engines.
So they're completely useless.
Right, completely useless. But the dealership still had to pay for the entire fleet of 100. With early 2-nanometer manufacturing, the defect density is just incredibly high.
I was reading that trial yields are only sitting between 60 and 70%.
Exactly. So you're paying 50% more for the pizza, basically.
Yeah.
But you have to throw away a third of the slices.
Oh, yeah, that's rough.
So when you factor in the $30,000 wafer price, alongside those lower yields, the actual cost per individual working chip jumps by roughly 80% compared to 3-nanometer.
80%.
Yeah. And the buyers just have to absorb that.
But wait, why would they? If you're Apple and someone hands you a bill that's 80% higher per chip, why not just walk away? Wait for the price to drop, or just take your money to a competing foundry?
Well, because there's literally nowhere else to go.
Yeah.
The latest data shows that TSMC basically holds monopoly pricing power right now.
Because Samsung is struggling.
Right. Their main competitor at the leading edge is Samsung. And Samsung's yields on their 2-nanometer process are reportedly stuck in the mid-50% range.
Which isn't enough. You generally need to cross the 60% threshold to even consider stable mass production, right?
Exactly. So until Samsung can sort out those defects, TSMC dictates the market. If you want the most advanced silicon to stay competitive in AI, you just have to pay the $30,000 toll.
Man. Okay, so if TSMC is operating as a functional monopoly right now, the market desperately needs a challenger. And it looks like we might finally have one with Intel.
Yeah, Intel Foundry is making some huge moves.
Right, they just announced at the VLSI symposium that their 18AP node has officially entered risk production.
Which is a critical milestone. Risk production essentially means a foundry is confident enough in their new process to start manufacturing actual customer designs.
So they're absorbing the financial risk of failures before ramping up to high volume.
Exactly. And Intel's 18AP node, the P, stands for Performance Enhanced, by the way, is bringing some seriously aggressive engineering to the table.
Yeah, they're using ribbon FET, which is basically their specific version of that gate-all-around transistor stuff we just talked about.
But the real game changer there is this technology they call Power Via.
Oh, the backside power delivery. I've been reading about this, and the concept is just wild.
Right. It completely flips chip design upside down.
Literally. Because for decades, the industry has built chips the same way we build cities. You just cram the highways, the plumbing, the power lines, all the traffic onto the exact same surface level.
Right. On a chip, that means the power routing and the signal wires are all just tangled together on the front of the silicon.
Which causes microscopic traffic jams.
And electrical interference, yeah. So Power Via takes all that power routing and moves it entirely to the back of the silicon wafer. It physically separates the power delivery from the data signals.
Wow.
Yeah, so by clearing out that traffic jam, you leave the front of the chip entirely dedicated to signal wiring.
And the performance metrics on that are pretty hard to ignore.
Oh, absolutely. By routing power through the back, Intel says they can cut dynamic power consumption by up to 15%. Or, alternatively, they can push 9% higher performance at the exact same power level.
Which is huge. I mean, when you're talking about massive data centers running thousands of AI chips, a 15% reduction in power consumption, that translates to millions of dollars in electricity savings.
And way easier cooling requirements, too.
Exactly. And this isn't just an engineering victory. I mean, it's a massive strategic play. We constantly see reports about companies looking to diversify their supply chains to avoid concentration risk.
Right. If your entire product line relies on one supplier on one island, you are incredibly vulnerable.
So Intel hitting these 18A milestones really proves they can execute on these complex new architectures. It validates them as a viable alternative foundry located right in the United States.
And the geopolitical implications of that are just massive, especially when you contrast Intel's approach with what's happening in China right now.
Oh, absolutely.
You've got the U.S. and Taiwan daddling over next-generation architectures like backside power. But then on the mainland, there is this massive, heavily sanctioned engineering effort happening under completely different constraints.
Which brings us to this fascinating teardown of Huawei's Kirin 9030 chip. So this is manufactured by China's SMIC on their third-generation 7-nanometer process. And when they put it under an electron microscope, the teardown revealed that SMIC actually managed to achieve a 32.5-nanometer metal pitch.
Which definitely caught a lot of people in the industry totally off guard.
Because 32.5 nanometers is actually tighter than the 36-nanometer pitch on Intel's cutting-edge 18A process.
Right.
Before we get into how they actually pulled that off, can you explain what metal pitch actually measures and why you should care that a sanctioned Chinese foundry is beating Intel on this one specific metric?
Sure. So metal pitch is essentially the distance between the microscopic wiring tracks on a chip. Think of it like the lanes on a highway.
Okay.
The tighter the pitch, the closer the lanes are, which means you can pack more transistors into the exact same amount of space.
But there's a catch, obviously.
Always a catch. If the lanes get too close together, the electrons flowing through them start to interfere with each other. It increases resistance. So Intel actually made a deliberate choice to relax their metal pitch to 36 nanometers. Because they used that Power Via backside power technology, they freed up so much space on the front of the chip that they didn't need to cram the signal wires so dangerously close together.
So they basically achieved high density without the electrical interference.
Exactly. But SysMIC doesn't have backside power delivery, so they basically just forced the wires closer together.
And they did it without access to the best equipment, which is the crazy part. Because of the U.S. export controls, SysMac literally cannot buy those extreme ultraviolet, those EUV machines from ASML that TSMC uses.
Right.
So how are they physically printing wires that are 32.5 nanometers apart?
Well, they're using older deep ultraviolet or DUV lithography machines. And they're leaning heavily on a technique called quadruple patterning.
Oh, wow. Quadruple patterning.
Yeah, imagine you're given a highly complex microscopic drawing, and you're told to trace it perfectly. But your pen is too thick to draw all the lines at once. So you have to trace 1/4 of the lines, then you get a new piece of tracing paper, align it perfectly, and trace the second quarter.
And you have to do this 4 separate times.
4 separate times, layering them exactly on top of each other without your hand slipping even a fraction of a millimeter.
So if you misalign even one of those 4 passes, the entire circuit is just broken.
Yep. That is the reality of quadruple patterning. It requires extra masking, extra exposing, and etching passes for every single critical layer of the chip.
That sounds like a nightmare for yields.
It is. Every pass introduces a new opportunity for a microscopic error. It's this brilliant, brute force feat of engineering to make it work at all. But the economic cost is just severe.
Because of all those extra steps, I saw reports that SMIC's yields are hovering around 20 to 40%.
Right. They're throwing away the majority of what they produce.
Yeah.
And furthermore, despite pushing that metal pitch to the absolute limit, SyncMic's overall transistor density still trails Intel's 18A process by about 38%.
It's just a crazy study in contrasts. You have Intel using elegant new architecture to solve the density problem, and you have SMIC pushing older DUV machines to their absolute physical breaking point just to stay in the race.
Yeah, and SMIC's reliance on those older machines perfectly sets up this huge geopolitical dispute regarding the next generation of chip-making tools.
The enforcement of export controls is seriously tightening right now, and all eyes are currently on just a single company in the Netherlands, which is ASML.
Right, because of the missing machine drama.
Yeah, there was a major report this week about a meeting between the U.S. Commerce Secretary and ASML leadership. And supposedly, the U.S. expressed direct concern that a top-of-the-line EUV lithography tool might have been diverted to China.
Which would be a massive breach of U.S.-led export controls.
Huge breach. But ASML's response was completely immediate and categorical. They completely denied the allegation.
Right. They pointed out that they track every single machine they build. Like, EUV machines are not exactly something you can slip into a shipping container unnoticed.
No, they're the size of a school bus.
Yeah. They require multiple Boeing 747s to transport and a whole team of specialized ASML engineers just to assemble and maintain them.
And ASML stated unequivocally that out of the 314 EUV machines they have ever produced globally, all of them are accounted for, and 0 are in China.
But it begs the question, why is the U.S. Commerce Secretary personally meeting with a Dutch company over a single machine? Like, why is ASML so critical to this standoff?
Because they're the ultimate choke point, right?
Exactly. They hold a total monopoly on EUV technology. There is no alternative. If you want to manufacture a cutting-edge AI chip or a 2-nanometer processor for a smartphone, you physically cannot do it without an ASML machine.
Which means this tension really shows how semiconductor equipment has just become a matter of supreme national security.
Oh, absolutely. We're seeing this shift from general oversight to basically a short leash policy.
Meaning governments are totally micromanaging the supply chain.
Yeah, they're actively revoking long-term certainty. Like export licenses for chip-making tools that used to be granted as these indefinite waivers, they're now being replaced with strict annual reviews.
Wow, so they want to constantly reassess.
Right. They want the ability to restrict or just cut off the flow of equipment based on real-time geopolitical shifts. Every major foundry and equipment maker is operating under intense, continuous scrutiny.
Okay, so we spent a lot of time focusing on the logic chips, the processors doing the actual math, but printing the brain of an AI accelerator is really only half the battle.
Oh, for sure. A brain is completely useless if it doesn't have any memory or if it can't quickly communicate with the rest of the system.
And the supply chain squeeze we've been talking about is hitting the back end of the manufacturing process just as hard right now.
The industry calls this the back-end bottleneck. And right now, memory and advanced packaging are proving to be just as critical and, frankly, just as supply-constrained as the front-end fabrication.
So let's break down the memory side first. There's data showing that we are in the middle of a massive memory supercycle. Contract prices for older memory types, specifically NOR flash and SLC NAND, have more than doubled in just the first half of 2026.
Yeah, and to understand why those prices are doubling, you really have to look at what those memory types do and what the fabs are choosing to prioritize.
Okay.
So NOR flash is incredibly fast at reading data. So it's mostly used for storing the firmware that boots up devices, like everything from your Wi-Fi router to automotive systems.
And SLC NAND.
That's a highly durable form of storage memory, mostly used in industrial applications. But here's the thing. Neither of these are used directly in AI compute
Wait, so if they aren't used for AI, why is the AI boom causing their prices to double?
because the massive semiconductor foundries have a really limited amount of factory floor space. And right now, the demand for high bandwidth memory, or HBM, which is required for AI accelerators, is just insatiable.
Ah, so they're converting the lines.
Exactly. Manufacturers like SK Hynix and Samsung are aggressively converting their factory lines. They're pulling capacity away from older legacy memory like NO and NAND to just churn out more HBM.
Which chokes the supply of the older memory, driving those prices through the roof.
You got it.
So let's talk about that high bandwidth memory, because the numbers associated with it are just crazy. On modern AI superchips, the HBM can account for nearly half of the total manufacturing cost of the entire unit.
Yeah, 35 to 47%. Easily.
Why does an AI chip need such expensive specialized memory? Like, why can't they just use the standard memory chips you'd find in a high-end laptop?
Think of it like this. Standard memory works like a single-story warehouse located down the street from a factory. If the factory, which is the logic chip, needs materials, it sends a truck down the street to the warehouse to get it.
Right, and that takes time.
Exactly.
Yeah.
But AI models, like large language models, are incredibly massive. They require a constant, unbelievable flow of data. If the AI logic chip has to wait for data to arrive from a standard memory chip, it literally sits idle. It starves.
So HBM solves this by taking the memory chips and basically stacking them vertically, like a skyscraper, right next to the logic chip.
Exactly.
And apparently, SK Hynix is currently shipping samples of 12-layer HBM4E to major customers. So they are literally stacking 12 memory chips on top of each other.
Yep. And then they drill microscopic holes right through the silicon of all 12 layers. They call them through silicon vias.
To run data connections straight down the stack.
Right. It's like building thousands of high-speed elevators directly from the memory skyscraper down into the logic chip. It delivers massive amounts of data instantly.
But building a 12-story microscopic skyscraper of perfectly aligned silicon has got to be incredibly difficult and expensive.
Oh, wildly expensive.
Which perfectly explains the final piece of this puzzle, which is advanced packaging. Because once you have your logic chip and your 12-story memory skyscraper, you have to physically wire them together.
And there was a major development on this front this week. Amkor and TSMC just signed a 10-year deal to provide advanced packaging and test services in Arizona.
And this deal is really the missing link for the entire United States chip manufacturing strategy, right?
Oh, 100%. Because the U.S. government is pouring billions of dollars into subsidies to get TSMC to build these massive leading-edge fabrication plants in Arizona.
Right.
But standard fabrication only produces the raw silicon wafers.
Right, like if you pull a 2-nanometer wafer out of the Arizona fab, you can't just plug it into a server.
No, you have to cut the chips out, place them next to the HBM memory stacks, and then mount them all onto a silicon interposer.
Which is basically a microscopic motherboard that connects everything together.
Exactly. And that process is called advanced packaging. TSMC's specific version of it is called CoWoS, or chip-on-wafer-on-substrate.
Okay, so if you don't have advanced packaging facilities in the U.S.,
Then you have to take the finished wafers from Arizona, put them on an airplane, and fly them back to Asia to be packaged.
which completely defeats the purpose of building a secure domestic supply chain in the first place. You've just created a multi-billion-dollar detour.
Exactly. And the packaging itself is no longer just putting a plastic shell over the silicon. It's a highly sensitive process.
It's become a front-end yield problem, hasn't it?
Yeah. Placing a delicate 12-layer memory stack next to a massive logic chip on a microscopic interposer requires extreme precision. If even a speck of dust lands on the interposer, or if the thermal expansion of the different materials isn't managed perfectly, the connections break.
And then you have to throw away a processor that costs thousands of dollars to print.
Right. So by bringing Amkor's advanced packaging facilities directly next door to TSMC's Arizona fabs, they are finally closing the loop and keeping the entire manufacturing process on domestic soil.
So, if you zoom out and look at everything we just covered, the thread tying it all together is the sheer force of friction. We are watching the leading-edge silicon supply chain get squeezed from every possible angle.
Yeah, no doubt.
You have the raw economics of physics, forcing TSMC to charge $30,000 for a 2-nanometer wafer. You have Intel attempting to break that monopoly with radical new backside power architectures.
And then you have SMIC stretching old DUV machines to the absolute breaking point in China, while the U.S. government basically watches every single ASML machine globally.
And all of this is happening while an AI-driven memory supercycle forces the industry to build 12-story microscopic memory skyscrapers just to keep the processors fed.
It's an industry operating at the absolute razor's edge of what is physically and economically possible. And honestly, it leaves you with a deeply unsettling question about the future.
What's that?
Well, if a 2-nanometer wafer costs $30,000, and advanced packaging is becoming just as difficult and expensive as printing the logic chip itself, what does the 1-nanometer era look like?
Oh, wow.
Yeah, right. We are rapidly approaching a point where the traditional Moore's Law method of simply shrinking transistors becomes too expensive to manufacture. Like, are we going to see a total reinvention of how computers are built simply because the current way is pricing itself out of existence?
It's a really profound thought. I mean, if the highly purified sand becomes too expensive to shape, the entire foundation of the modern tech economy will have to pivot.
Yeah, something to think about.
Well, thank you for joining us on this deep dive. Keep asking questions, keep looking beneath the surface of the hardware that powers your world, and we'll see you next time.